Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Uh. Yeah.
Hello, everybody. How are you doing? Welcome to another episode of Ask Us Anything About Electrochemistry. Please let me know if you can hear me. I always like to do a little bit of a technical check to make sure everything's working, all of those things. And welcome. My name is Dr. Alex Paroff. My colleague, Dr. Neil Spinner, is not with me today. He is actually traveling. He is in Missouri and finishing up a meeting at the a regional ACS meeting. So, welcome everybody to another episode of Ask Us Anything About Electrochemistry. This is where we, my chemists at Pine Research Instrumentation, try to answer questions that you may have about electrochemistry. Now, let me just want to wait a second. There we go. Let me see. I'm 5 and 5. Okay. All right. Good. Thank you, Chris, for letting me know that the sound and the audio is working. I only have somewhat limited feedback, but thank you. So let me actually do just one quick thing. I want to just make sure that it's coming in well, because I have to have the audio on here. Let's see. Okay, well, 5 4. Occasionally there's a glitch in the audio. Okay, all right, that's all right. As long as people are hearing me, I think there's always some kind of glitch in the audio. But I digress. I think I'm getting off of the point. So, with every episode of Ask Us Anything About Electrochemistry, you, as the electrochemist and the researcher, can ask me and any of my colleagues at Pine Research technical questions about electrochemistry. Electrochemistry is a very confusing, complicated subject, and more often than not, we we don't. They're just concepts that are not that don't that they're not really well described, or people just have a hard time understanding them, and that's what this session's for. We get a lot of questions from YouTube, from email, from webinars, and sometimes those settings are not always the best for trying to address these questions. Um, and that's why we have these sessions where we can really take a deeper dive into some of the questions that you may have as electrochemists. Uh, Oh, it's noticeable. Okay. All right. That's good. Okay. I need to make sure I have the mic. Thank you, Chris, for making sure I have the mic very close to my head. Okay. All right. Good. So we usually run Ask Us Anything sessions on Fridays around 1 p.m. for about 2 hours, depending on how many questions we get and the nature of how complicated they are and stuff like that. But I'm using Restream as the platform to show this information, to broadcast this episode, and we are on Twitter as well as YouTube. So if you're on Twitter, we're going to try to I'll try to check to make sure. If you have any questions, please let me know on Twitter. If you have any questions on YouTube, please let me know. There tends to be maybe a 20-second delay between what I say and when you receive something in the chat. That's something that we've observed over our time running these sessions. So just keep that in mind as we answer questions. And there are no dumb electrochemistry questions. All electrochemistry questions are good. I would only ask that you try to be as clear as possible and as specific as possible with regards to your questions, because sometimes questions like "teach me cyclic voltammetry" is a little bit too broad or too vague of a question um, for me to give you any real information or feedback and help you answer that question within a reasonable time frame. And sometimes I may actually refer you to another resource to actually do those more broad questions about electrochemistry. Um, this is we are on social media platforms, Twitter and YouTube. So if you ask a question and I don't get your name correct, forgive me. And also, I want to have a shout out to all of our tier one and tier two members on YouTube who support us and help make this live stream really possible. The content creation that Neil and I create is very much supported by the tier one and tier two members who just a little bit of support. Tier one membership is just $1 a month. Um, and that's it really actually goes a long way as we try to build an electrochemistry community, an online electrochemistry community. Um, and so as we wait for, I'm trying to think, there's usually one more thing. Also, if you are a tier one or tier two member, um, about 30 minutes before this live stream started, I sent a link into the YouTube community chat with a link that you can join us on Restream to ask your question. So rather than just typing your question in, uh, you can actually be on the platform live and talk to us, and even you'll be able to share your data, share screenshots of voltammograms or EIS, Nyquist plots to try to answer, to give us a little bit more information about your system, and it's very, very helpful. So tier 1, tier 2 members, there'll be a link. You can join us on Restream. That'll be broadcasted to YouTube and Twitter, and for the most part, we'll be able to answer any questions. So as questions start to come in, we'll wait for people to type their questions in. I just wanted to say last week I was at the ECS meeting in Sweden, in Gutenberg. There's many different pronunciations. I had a chance to meet some of you who attend the live stream. Sempa in particular, thank you for coming to the Pine Research booth. It was great seeing you and meeting you, as well as other people who have watched us either on the webinars or on the YouTube channel. It's great actually meeting you in person. I wish I had more like pictures from the event, but maybe later I can share some stuff. Um, let's see. So as we wait for questions, actually, Chris just threw a question out. I'll throw out some of an open-ended question. What sort of procedures would you use to study catalysis poisoning? That's a good question. I have to think a little bit about it. So catalysis poisoning, well, let me hold on. Let me share this. I gained a little bit out of practice. Chris is asking, somewhat open-ended question. What sort of procedures would you use to study catalyst poisoning? Um, I think catalyst poisoning, for the most part, is the example that comes to mind is like carbon monoxide poisoning, where some kind of molecule, some species, irreversibly adsorbed onto a catalyst active site, and it's no longer able to come off, and it blocks that site, decreasing the activity of the catalyst. I think when it comes to studying any kind of system or technique, you need to be mindful. Actually, let me put this back up. You need to be mindful of reproducibility. So when you have a procedure for doing something, for doing a catalysis study, you want to make sure that, well, does the activity of your catalyst decrease consistently from one experiment to the next? Now, another thing I would actually find with regard to catalyst poisoning is almost the same procedure I'd have for just about any experiment, which is if you think that your catalyst is being poisoned by a specific molecule, in a separate study, I would actually just add that molecule to the system in a controlled manner and see if that actually decreases its activity. So, for example, if over 10 cycles, I'm just going to make up some numbers, but after 10 cycles of using this catalyst, you start to see a decrease in activity. Well, perhaps if you believe that it was CO poisoning, you could add a little bit of carbon monoxide early on into the system and see if that uh, leads to a decrease in the catalytic activity to see if that's a thing. But if you have another, for example, if you thought something else was poisoning the surface, you could try to add it in and just see, do you get reduced catalytic activity? And those will start to kind of present information and models for understanding how poisoning is occurring. I would also say that um, I mean catalysis is really at least I always think about heterogeneous catalysis. So with heterogeneous catalysis, you have it's a surface science. So if you're looking at things like isotherms, surface coverage, using those surface techniques specifically for studying the catalytic activity, um, and the poisoning of catalytic sites and monitoring how the surface is changing, those are really going to be the methods I would think about for studying catalysis poisoning. Because once you realize, oh, it's this specific system or this specific chemical that's poisoning the surface, you can start doing chemistry and reactions that actually do that process. So it's not just studying catalysis poisoning, it's studying what is the chemical process that's actually occurring, what's the rate law, the kinetics associated with that specific process. So that's kind of my procedure or general process for studying catalysis poisoning. So hopefully, Chris, that was helpful. Open-ended question, but it's good. Let's see. Great. We have a question from Sahid Abi- Abiola. Good day. Please, how do we calculate the Q charge in faradaic efficiency for ammonia yield? For instance, the area below the curve by integration from chronoamperometry test. Could you elaborate? That's a great question. That's a great question, Sahid. So the process for doing this actually involves two steps. It really actually involves two experimental procedures. One is if you're doing an ammonia yield, some kind of reduction of nitrogen to ammonia or something like that, and you're trying to get a percent yield, you're trying to get a faradaic efficiency out of it. So if you hold the potential, and let me share my screen, and hopefully I can get some more um, help you a little bit more out with this. So let me also just make sure that my screen is being shared. Oops, sorry. I'll show a little bit of my face so that you see stuff. So let's just do something very simple. Um, and we're going to have some kind of ammonia yield. So I'm imagining you're looking at a reaction like N2 plus, I don't know, like H2. And I think there's about, and let me make sure I get the stoichiometry correct. So you're forming NH3. So I believe for two, you need three of these. So six, yeah. So two of these. So this is the reaction. You're trying to form ammonia. And well, let's just say this is an electrochemistry process. So you have some electrons. So instead of hydrogen, you actually have electrons plus protons, right? And there's some stoichiometry associated with it right now. And let me actually make sure I get this right. So because I'm trying to think through this problem with you. There's a couple things that you need to keep in mind when it comes to looking at calculations of the ammonia yield. So there are going to be 6 H plus, and there's going to be 6 electrons. So this is the electrocatalysis reaction that's going on. Okay. Now you're doing an experiment where you are holding the potential. Let's say you're holding the potential. You say chronoamperometry, so you have your current, and you have your time, and this is like almost like a bulk electrolysis experiment. So let's say time equals 0 is here, and then you step the potential, and then you got this decay. The decay never goes back to 0. And so you let this go for some amount of time. And you know that the area under the curve, let me use green, but you know that the area under the curve represents the charge. And you can calculate that. You can use your software to basically use some geometric tools to calculate the area under the curve, and that area under the curve gives you Q. So Q is the charge. Now, what I think you already know is that the what I think you already know is that the charge can be related to the number of moles or sorry, what I meant to say is I think you know that the charge is not all of this charge, not 100% of the charge is all faradaic. It's not all this product. Some of it is going to things like uncompensated solution resistance. Some of it may be going to side reactions. You may be forming hydrogen gas. That's not very good, right? So you can calculate the total charge, but you know fundamentally that not all of it is going into ammonia production, your ammonia yield. So what you end up doing is you do a separate experiment. You're using a GCMS, some kind of gas chromatogram, mass spec. You may even be using HPLC, high performance liquid chromatography, HPLC. So you're using these techniques to actually give you the number of moles or grams or some quantity. Oops, I don't want the mole. So you're getting some kind of moles of ammonia, and you can see it because in your GCMS. I'm not an expert at GCMS, but it's like mass per charge, and you get some lines. But one of these lines, this is quantity. This is some relative quantity. I don't remember the units, but some quantity. Not actually. I don't want to use quantity. I want to use some other numeric thing. We'll just call it just kind of arbitrary units, just number of things. But you know that this peak over here is associated with ammonia just based on its mass charge and how and what it is. And you can determine this through other techniques or control studies. So this will give you some number of moles. When you use GCMS or HPLC, you're able to get a number of moles of ammonia that was generated. So you know what this is from this technique. But you can also figure out how many moles should you have gotten from your chronoamperometry experiment. Okay. So, oh yeah, and actually, I'm just checking. Chris is saying aqueous or gas phase. So that's a good point, Chris. I don't know whether it's going to be aqueous or gas phase for this, which is why I'm saying HPLC or GCMS. Now, the thing is, so when you take the charge, converting the charge to moles is actually quite easy. The thing to keep in mind is that, oops, the thing to keep in mind is that it's based on charge. It's like NF, right? So this is the number of electrons. I think it's like Q. Q is NF. But basically, the Faraday's constant relates the charge in coulombs to number of moles. So you're able to do a little bit of math, but the key to remember is that your n, oh wow, that was terrible. This n is 6 in this experiment. So you have to make sure like that the number of moles that you should get from a chronoamperometry experiment is based on this 6. Like, you have to know that this is 6, because otherwise your calculations are going to be off. This can't just be like 1. So you need to understand what the fundamental, not the fundamental, but the total number of electrons transferred for this reaction. And this reaction is very, there's probably many, many different steps that are happening in this reaction, but the total number, the 6 electrons, is what's important. So make sure that you're able to, I think, take, let's see, so charge. Let me actually just make sure I have the units right, and then I'll start getting to other questions, or more importantly, ask you for if you have any further clarification. So charge is in coulombs, and make sure I have, so then you have number of electrons, and then Faraday's constant is coulombs per mole. So what you're going to need to do is you're going to have to basically divide coulombs. You're going to need to take coulombs divided by Faraday's constant, and then also you're going to need to solve for the number of moles, and moles will be kind of, when you do this math, you're going to get the number of moles out. So at the end of the day, I know this is a long way, but you're going to find some number of moles here, which is going to be your theoretical maximum. The number that you get here is going to be the theoretical, kind of like 100% maximum that you can get. But this is going to be the thing that's going to tell you what you actually get. So this is going to be some fraction, and that's going to tell you what your faradaic efficiency is. And you're going to assume that there's going to be losses for other processes. Um, so um, so Sahid, please let me know if that was helpful and if I answered your question, and if you have any further questions or clarifications. All right. So hopefully that was good. Let me do a quick look to see if there's anything happening on Twitter. Nope, nothing happening on Twitter, because no questions come, rarely do questions come in there. All right, moving forward, I'm just looking at questions. Kashitij, Kathat, sorry, again, if I'm mispronouncing questions. Sir, after circuit fitting of Nyquist plot, if some calculated values come off too large, then what should I do in that scenario? I work with electroactive bacteria, so my system has biological entities. And let me see. There's a little bit of follow-up conversation. I just want to make sure I'm not missing anything. Appreciate data moleys, a lot of complexities. He just wants to get an opinion. And then this might actually have to do with the previous question. All right, so going back to this question, after circuit fitting, basically you're trying to determine when calculated values come off too large, what should you do in this situation? And not knowing anything else about it, I don't know. So usually you need to, I think, somewhat to echo Chris's point, is think about the circuit. If you're very confident about what the circuit model is, this is an assumption, you may want to change the circuit model as long as it's fitting reality. And you also want to evaluate whether or not how good of a fit it is. Now, if if you're confident of the circuit model, and if you are confident, and if you have a great Kramers-Koenig relationship, your chi-squared is very low, and you believe it, and visually it looks like you have a very good fit, but you're getting some values that are really large, what should you do? Well, I think what's important is if those values that you're getting for your bacterial system are consistent, in the sense that they're reproducible, it's not a fluke value, you will need to think about what does it mean? What does it mean physically? And sometimes you may have to actually say, like, okay, this thing is like 10,000 times higher than what it could really be. Well, sometimes that may indicate like, oh, there may be something wrong with the circuit model that you're using, but it may also be indicative of a totally different mechanism or a different process that's occurring. I'm almost certain that the first time people were looking at the capacitance for the electrical double layer, the fact that they were getting something like 25 microfarads of capacitance for this little, really, really, really tiny thing was super, super complicated. Like, I had no idea, why is this the case, right? That's almost the nature of science in and of itself. Why do we get these results that are different than what we would have predicted? So, to a degree, as Chris said, bacterial biosystems are very complex, and you may be dealing with a very complex impedance system where, it really is a very high resistance or a very high capacitance to have charge transfer occurring through parts of your biological system. There may be unique interfaces at play, um, or even indicative of gaps. Let's say maybe you model something, it's not a capacitor, it's a resistor, but there's actually an air interface in your biological system. Well, the resistance of air is super, super high. So that may be another thing to think about. So this is all a lot of speculation about what your system is. But that's what I would say. I would say, if you're very confident in the values that you're getting, they are reproducible, and you're confident in the fact that, okay, they are correct, but you don't know why it's so high. You have to think about why scientifically would it happen, and you may have to even do other experiments complementary to EIS to gather more insight as to why it might be happening. So, Kajitij, sorry if I mispronounced your name. I hope that was helpful, and please let me know if you have further clarification, or more questions after that. I'm very happy to help with that. Okay, so Zahid is just giving me a follow-up. Thanks. It was for nitrate reduction to obtain ammonia in aqueous solution. I tried to obtain the integration of the curve on origin. I want to be sure if it is correct as well. Oh, Sahid, so this is a great point, great thing. Thank you for telling me it's nitrate reduction. That means your chemical system is actually good. Let me show you. Let me show you one thing that might be very helpful, potentially helpful to you. And of course, I'm going to I'm going to share our aftermath software, for example. So right now, this is our aftermath software, and let me see if I can find some sample data. Let me see if I can archive this. This is just a cyclic voltammogram. This is a CV simulation. All right, so I have current versus time. This is the current versus time plot. And this is data that you could import into our aftermath software. So I know you're using Origin right now, but in this case, we're looking at a reduction reaction. And let's say I wanted to figure out what the area under the curve. I could use our tools. So I'm using area tool, clicking the area, and I can actually make some adjustments to try and get the calculate. Oh, what's the area for my system? Oh, sorry, I just sneezed. And so you might say, oh, well, I want to figure out what the area is, and I get a value like this. Sometimes the area, the charge for your system, it might come off a little weird. It might come up a little off because of how we inherently calculate it. So, are you calculating the charge under the curve based on um, based on just the geometric area, or are you basing the charge off of the difference between negative and positive current? So let me actually see. I think say more and more negative current. So this case, so for example, in aftermath right now, the current or the charge is based on the total negative current. So even though I have current here that's positive, when it gets added to this area here, I'm getting a larger negative charge that's passed. So and that may be a thing to consider and think about when it comes to determining the charge. So you can download Aftermath software for free off of our website, and you can actually just plug your data in, use this area tool, and it'll automatically spit out what the charge is. And you can use that to double check whether or not the area you're calculating in your chronoamperometry experiments are indeed correct, or at least you have something that you can double check it against. Okay, so let's go through. All right. I definitely enjoy a good conversation. Let me see. So Gojit, just following up. Fit is good, but can you please tell me a range of good chi-squared values? By the way, I have reproduced data in triplicates. Okay, very good. So it's funny. This is a fairly triggering topic for Neil. It's always very funny when we both have our triggering things, which is what is a good chi-squared value? And every Sahid says thank you. You're very welcome, Sahid. Um, I don't actually know a very good range of chi-squared values. I've seen chi-squared. What Neil has told me is that chi-squared on different potentiostats, different circuit fitting softwares, will actually be different based on how it's calculated. Um, Small subtleties in the algorithms and the math that's used. Now, I've seen chi-squared values, I think as long as you have maybe like zero point 0.1 to 0.0001 or something like that, that's, I would say, a good chi-squared value. Remember that chi-squared represents kind of the deviation, the average deviation between the fitted and the theoretical values. So really, what's almost better to do is to just visually look at your EIS data. And I don't have a good, sorry, I don't have a good like plot, sort of say, but I can show you. Let's just do like I'm gonna do some pretend EIS right now. So you got a Nyquist plot that looks like this. I'm just guessing. Actually, let me. So you got a Nyquist plot that looks like this. You got these values that what you get is this. These are data points, right? They're data points. They're spaced out in a very interesting way. And then you do your fit, and your fit is like continuous. And I'm actually going to do what I don't normally do, which is I'm going to change the kind of the boldness or the thickness of this line. So it may not be as easy to see, but it's kind of easy to see. All right, so this is actually, I think, fairly well. So chi-squared is really looking at this difference, right? It's looking at this difference between your data point and the circuit fit. And it just spits out a value, right? It's spitting out this value of like 0.1 or, and or 0.0001, or it's spitting out a value that's terrible, some things like 10 or 100. And interestingly enough, you may find that, hey, the fit here is awesome. The data points line up really, really well to the theoretical for your circuit model. But then over here, you get all these big deviations, and your chi-squared value is going to just spit out a number that takes into account this, and this. You may, if I, as a scientist, I would say, hey, my this almost never happens. My high frequency data is actually pretty good, has a really good fit. But then like my mid to low frequency is actually not so good of a fit. I might decide to either like redo some parts of the experiment, like maybe even do like a low frequency EIS, just trying to get, really make sure I have this correct. And I may do a little bit more circuit fitting and a little more adjustments to get just to get it to look better, something satisfactory to your eyes. So chi-squared, it's helpful, but it's really hard to say like, oh, this chi-square value is good, and it means that all your data is good. One data point, one outlier, you may have something like this, where you have data points and outliers that are like way off, and that's making your chi-square value incorrect. So, if you omit these points, like if you just omit them or weight them differently in the circuit fit, you'll actually get a better chi-square value, and that may actually help adjust your values a little more, a little better. So hopefully that's helpful, or gives you a little bit more clarification about how to approach circuit fitting and the values that you're getting. All right, moving on. Let's see. We have Ashwin. And actually, let me also just take a quick look. Anything? It doesn't look like anything on Twitter. I'll have to double check. Okay. Ashwin asks, "Hey, I have done EIS of multi-component coatings on copper substrate, but it shows inductor in, let's see, RQR. I think that's just a way of describing um kind of the flow. I'm assuming that this is like you kind of have a strong embedded system. Is that correct, Ashwin? Um, so just it's showing a strong inductor in RQR. Okay, so that may be the case. Is there a specific question about it? You may actually have, I don't want to say inductive effects. I'm learning more and more about inductors and the role that inductors actually play in EIS, and inductive loops, which are still kind of triggering. So, but multi-component coding. But usually, actually, when you see inductors, I have learned this. When you see inductive behavior, and just to kind of show you what I mean by that, when you get these kind of loops in your system. Let me see. Let me get rid of this. But when you get these kinds of inductive loops, I'm still really learning more about this. But this is your Z real, and this is negative Z imaginary on your Nyquist plot. You sometimes get stuff that looks like this. Maybe you have this, and then maybe you have something like this. You have this kind of inductive behavior where you have, or in other cases, you have maybe something like this. It curls, or actually, I don't think that's actually. I actually don't know what that is. But I've definitely seen very strange curling behavior. But you may get something like this, or it'll show up underneath, like here. So it's not, as what I've learned about how you get these inductive effects, and please correct me if I'm wrong, Ashwin. What I've learned actually about some of these inductive effects. Hey, Neil, a wild Neil appeared.
I made it. Can you hear me?
Let's see. Oh, I
Can
think
you
you're
hear me?
talking, but I have my volume off, but I will.
Okay.
It's okay.
Somebody, can anybody hear me?
Let me make an adjustment because hold on.
Check, check, check. Audio output. Wait, that's me. It's me. It's
Oh,
me.
I
I got
can't
it. Can you hear me now?
tell if it's-
Can I be heard? Hello, test, test.
Anyway, I'm just gonna be basing it on whether or not I I see your lips moving for now.
Yeah.
But for now, one thing I've learned about these kinds of inductive behaviors just in the reading is that when you have codings, multiple codings and stuff like that, inductive behavior actually is the result of different electron transfers within the coding. So if you have one layer, and you have, say, another layer, but it doesn't. There is no capacitance here, so you don't have a capacitive effect. Actually, I should try this. Like you don't have a capacitive effect. All right, we usually think about this, but if you don't have a capacitive effect and you just look at electron transfer, then the surface coverage of that electron of that coating, and depending on the kinetics of the coating going from one thing to the next, will actually play a role. So I've become less surprised about inductive effects as a result of that. But again, you actually don't have a question per se, and let's get Neil here. But hopefully that's very helpful.
Can you hear me yet? Alex, can you hear me yet? Check, check. Can anybody hear me? Is it me or is it you?
You can keep talking, Neil, as I try to get
Yeah, tell me
audio.
if it's you or it's me. Someone in the chat can say if you can hear me. That would be helpful too, because I think it might just be Alex. Delayed bleed through audio. Of me or of Alex or of both of us? I might have to leave if this is ruining everything. Hang on. Check, check. Test. Trying to change some of the settings here. I think Alex can't hear me, but you can hear me. Chris can hear me. This is what happens when we do this from different locations. It's not ideal.
All right. Just bear with us. Or bear with me. All right. Well, Neil's audio is coming through. It's just I can't hear it because of my headset system right now. I may, you know what? I'm actually going to double check to make sure this is plugged in correctly. So luckily we don't have too many.
So everybody else can hear me and Alex can't, but I can try to answer. Chris, you can hear. I assume that I am being heard right now, so I'm going to plow forward assuming that. Otherwise, you're just looking at my lips moving. But Kshitij, I think you were just having some of your EIS questions answered, so obviously I popped in a little bit late here. I am on the road. You're asking about some reading materials for EIS. So there are basically, to my knowledge, two really nice textbooks on impedance. Okay, and let me share my screen here. So, for example, this one here by Mark Arazum, he's a professor at the University of Florida. This is a terrific book. So this is a good one that has a really good basis for impedance. I recommend this book. And then as well, there's another one by Lasia. So these are kind of like, at least in my estimation, the two, resources on impedance for textbooks that I guess I would recommend. So Lasia and then Orism. I have the Orism one, which I like. And then I suppose a shameless plug for ourselves is that I have a webinar that I've done in the past on impedance, and it's on our YouTube channel. And if you're a tier 2 member, you can watch all 5 parts of it. Can you hear me now, Alex?
Yes, I can.
Oh, cool.
I needed to go to the Focusrite control, and had my audio on mute for some reason, or my headphones on mute once I turned it off.
Yeah, sometimes I mute this is insider baseball for everybody else, but yeah, sometimes I mute both of us when we're doing it, like because I'm playing the live stream waiting video and we don't need it in our ears and stuff. So yeah, so I'm surprised because like my computer has that saved for you.
Oh,
And then my computer's with me in Missouri and
yeah.
in North Carolina, so I don't know why it's remembering that setting. But anyway, the point is those 2 books are good, and then our webinar series on impedance on our YouTube channel is a pretty good, and it's obviously it's visual. If you don't want to have to sort of sit through a textbook, if it's a little bit, I don't know, it can be kind of dull to, sit there and read a textbook maybe. So if you wanted video content, we do have a lot of resources on impedance on our YouTube channel and on our knowledge base as well. I've done some derivations of the mathematical basis for impedance, and then Alex has a really nice some illustrations and some animations on our knowledge base for like basics of impedance as well as a YouTube video. So. And keep joining us on Fridays and ask your questions. I don't know what you asked prior to me coming, something about inductive loops, and I think there was a chi-squared thing, so I'm glad I missed that.
Yes, you did. It's the typical question. How do I know if it's a good chi-square value? No, it's just like, oh,
you
man.
Don't use chi-squared, it's useless. No, I'm just kidding. Chi-squared is my trigger point. So we got chi-squared and inductive loops in the same live stream. This is definitely not our day.
Yes. Well, as we wait for some more questions, I think I got most of them, unless you want to comment. I didn't know very much with Ashwin's question. Just, I guess this is the formulation of this is kind of just the formulation of like how the circuit is supposed to look. I think this is just like a really embedded like CPE resistor, CPE resistor. I'm not too sure how to interpret it.
Well, okay, so I mean, I can try to share
if you want to.
Yeah, this is a tricky kind of a thing. So I've seen this sort of representation before of a circuit. What I can do is let me pull up our software, and then I have to share the right screen, because every time I share our software and then I make a circuit, it's like.
Oh yeah, there's another.
It doesn't. It's like a different window. So let me get to the right thing really quick here, and then I can hopefully share what I'm understanding. Okay, I have it here. Yeah. Give me 1 second. I'll find the thing to share. Designer. This is the one. All right. Am I showing the circuit fitting thing?
Yeah.
All right. So effectively, what I'm guessing you're talking about is something like. This would be like a normal, forget about the lack of connections here, because I'll connect it in a second. But if you have like a Randall's element, right, you have resistor, CPE, and parallel, okay, and everything's all good and happy. But what you're talking about is that you have something like, typically what you have is a CPE in parallel, and then you would have an embedded one. So something like this. This is like an embedded model. It's going to look a little strange until I move stuff around, so bear with me.
Oh, yeah.
I think, hang on, I drew this wrong. Like a dummy.
It's all good.
Like a dummy, I tell you.
This is just very complicated.
I'm trying to. Okay, so here's your simple Randall's thing. Sorry, I will fix this egregious error. So basically, it's like you have another embedded Randall's element in here.
Oh, okay.
Okay, so something like this, and then you can just take this to the nth degree, and this is kind of what. Let me switch these. So it's like, this is like an embedded model. It's kind of like two Randall's elements, except the lines don't always. I wish it would stay flat and straight. It's just like the way it works. Anyway, so this would be like the next stage of the embedded model. Okay, So you have like this Randall's element is this one. See, I know it's like ugly. Try to move it. So there we go. So it's like,
Oh.
here's one Randall's thing, and then here's one embedded down here. Now you can take this another step. So again, this is what I was trying to cascade this out. So it's like, now you're talking about like yet another Randall's element embedded in here. And so you can take this on and on. Now, when I talk about embedded models often, and in some of my webinars, I've done this, for example, yeah, I know it's ugly. It never like arranges itself. So this is kind of like almost like a 3-tier, and then you could just keep going. You can take like an n-tiered, you could do another one if you can imagine this going down and down and down forever. This is a tricky situation because in some sense what you're doing, it's a bit complicated to talk through. So I'll try to describe it in words, but you'll have to sort of bear with me, and please comment if you want more specifics to this. But in the interest of my ability to describe it in this venue, I will have to oversimplify. You're actually in this model doing 2 things. One is you're implicitly neglecting a series of resistors and capacitors that may be neglectable, but they may not. Okay, so this is kind of like a not full embedded model. I'll bring up a PowerPoint to kind of illustrate what I mean. But as well, you're showing this embedded kind of structure, and you're assuming that it's like, which may be the case, but it doesn't necessarily have to be the case. You're assuming that each layer is embedded like only in the next one, instead of like you're assuming one particular structure, sort of like one thing on top of another, and that may not be the actual microstructure of your electrode. It might be more complicated. There may be sort of an amalgam, if you will, of different layers, and so this might not be perfectly appropriate, it quickly can get cascading kind of out of control. And in some ways, this type of model almost, I don't know how to put it, it can almost resemble kind of like what the Kramer's Kronig is like, where you're just adding endless Randall's elements. It almost fits. Well, there's a little bit of curvature. It's not fitting. I add another Randall's element, another embedded element, and I just continually add more to make it fit. But eventually you just have diminishing returns from the perspective that like, this doesn't mean anything. I'm just adding more embedded models. And so you sort of run into that situation where eventually, what in the world does this actually mean? And the answer is probably nothing. So you got to be careful, as I try to sort of vaguely advise rather often. You have to be careful about over specifying your circuit fit to the point that it no longer has any reference in reality or any kind of phenomenological process. Okay, so let me share one last thing to this point, and it's part of a webinar I had given in the past to sort of illustrate what I meant by you're neglecting certain components. So this is an example that I had done previously of like a triple layered corrosion. Customer had given me some data. For example, you see there was like a steel, and there was this galvanized steel layer, which is like some kind of zinc iron alloy. There's some biopolymer coating, and there's like electrolyte. So you basically had something like 3 or 4 interfaces. Okay. And so you can imagine each interface can be accompanied by a Randall's element. Okay. But what if this microstructure isn't simple, right? This one on the right, the microstructure is like electrolyte can reach all the way to the bottom, or maybe it can reach to the sides. You might have extra ones. So this is where that embedded concept comes from. You see that there can be some variations in this. So when you're just adding another embedded model, you might be sort of making an assumption incorrectly, perhaps. And then the embedded model, I want to see if I have it sort of laid out here. So the one of the ways that the embedded model looks, for example, is actually a derivative of this model right here. Okay, so the one that you're probably more commonly looking at when you maybe see it in a paper is where I'll black some stuff out, sort of, to sort of mean. This isn't there, okay? And this isn't here. Okay, so the typical kind of embedded model might look more if like this, where you have this CPE over here and this resistor. And so often these two are treated like their own couple, but you can see what I've actually done is hidden their respective Randall's components. And it's because often this capacitance that I'm covering up right here can be neglected because it's capacitance between solid layers, which is pretty negligible. And this resistance can sometimes be neglected as well because maybe there isn't any faradaic process occurring here, you just have double layer. But that may not be the case as well. So I hope that's somewhat of a, I don't know, summary of a bit of that phenomenon where you just have RQ, 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 and you just keep embedding. It's an interesting take on some phenomena, but it can be buried in there some assumptions that may not be accurate. So, and then I guess, sorry, the last part of that was that you had an inductive process in there. Well, frankly, you can't capture that with just R's and Q's. So if you do have some inductive process, I think Alex, you talked about the inductive loop thing, your favorite, a bit. And so that would require a different model, right, with the three-tiered one, if you showed that. I think you did. So anyway, there's a bit of insight on the embedded thing, for what it's worth.
Good. Hopefully that was helpful to Ashwin with their question or comment. So we have another new question from Murray Moose. How can I use chronopotentiometry to analyze zinc oxide semiconductors, conductors in this case? And I think it depends, to answer this question, it depends on what you want to learn or study about zinc oxide, and also the nature of the zinc oxide itself. Like, do you have just like a pure flat zinc oxide, or is it a nanostructure, or what form is it in? But chronopotentiometry is a technique where you set a constant current and you measure the potential as it changes. And so the system that the semiconductor is in is also going to change things. One thing that I have always kind of struggled with and don't have the best conceptual understanding of is kind of the band gap structure of semiconductors in general. And they exist one way in air, but they exist very differently in solution. So I'm assuming this is like chronopotentiometry. They're in solution. Is the zinc oxide doped? I mean, in the most general sense, if you apply a current and you measure a potential, you're learning at what potential do you drive current through your semiconductor system. And I don't know, Neil, if you want to comment a little bit about using chronopotentiometry as a technique.
Yeah, I mean, it's a strange choice. I guess my follow-up question to that, which is kind of a general question, is why do you want to do chronopotentiometry? You know,
yeah.
Why? What's the purpose? Because quite frequently with materials, you want to control the potential, because the potential is what determines the thermodynamics of what you're, based on whatever E0 you're trying to study or whatever. And as a semiconductor, semiconductors have a lot of different applications and purposes. So if you're trying to drive a certain amount of current, like the purpose of a chronopotentiometric experiment is to, I want to drive like 2 milliamps out of this thing or whatever. It's like, but why? For what? Mm-hmm. And you might be wildly altering the the potential of that semiconductor to be doing other reactions, so that current might not be related to what you're even trying to study. Like chronopotentiometry is a very strange choice, in my opinion, for a semiconductor. And I guess, yeah, the follow-up questions from us, I guess, would be, why do you want to use that, and what are you trying to study precisely?
Yeah, yeah, I agree. Let us know, like what do you want, and then we can figure out what's the best technique or approach to actually solving it. Well, let's see. We just got a new comment from Ben, but actually, before we get to Ben, let's see. Murray has a follow-up. Let's see. CP is used to determine the charge-discharge behavior of photocatalytic materials.
Well, if you're doing charge discharge, that's a potentiometric experiment. But photocatalytic. I don't. I mean, what kind of a cell is this? Is this a capacitor or a battery or something?
Yeah, like zinc oxide semiconductor. I figured you might be using this more as a. And you say photocatalytic materials. So whenever I think about charge discharge, I'm thinking about batteries. I'm just thinking about you're charging something
Yeah.
up, you're gaining charge on one side, and then you're eventually going to discharge it later. Which you're right. Chronopotentiometry is the way to go for doing something like that. But that's
Right.
studying batteries most of the time.
Yeah. This situation that you're describing is a little bit is a little odd. I guess I don't know what's the charge and discharge of a photocatalytic. Like, what's the cell? What's the system? And I guess specifically, what is your question? Like, it's sort of like, how can I use it? It's like, I don't really understand. I mean, are you asking how you like calculate, or like what? This question seems quite general. I guess I don't really understand what you're asking. How can you use chronopotentiometry for charge discharge? It's like that you're sort of answering your own question. You apply a positive current to charge something, you apply a negative current to discharge it until the voltage hits something. That's typical charge and discharge behavior. So if you're asking specifically something else, you'll have to specify.
Yeah, I also would say somewhat limited knowledge, but unlike techniques like cyclic voltammetry or EIS, where you can extrapolate fundamental information about the material, like, oh, I now know what the rate constant or diffusion coefficient of a thing is. I don't know if chronopotentiometry will give you that kind of information. But let's see. Chris actually has. Let's see. We have a little bit more. Murray's saying used as photocatalysis for photodegradation process. Okay. And then Chris is also giving a comment: excitation state time constant of material versus photon flux. So there definitely needs to be light in this process. So yes, how can I? So right. So if you're using light in this kind of situation, I might suggest, like, oh, okay. Here's another way of thinking about it. So actually, the way you're probably going to use this is you're going to try to hold a constant current. Maybe it's not even a lot of current, and you're just measuring the potential as a function of time. And then when you shine light on and off of that system, the potential is going to change. And that's really what, that's actually how you would use chronopotentiometry. So I'll just kind of share my screen and hopefully kind of maybe demonstrate a little bit. Hopefully this is helpful. But what people usually do is they have these experiments. This is your let's see, am I sharing it?
Yeah, you're good.
Yes, I am sharing it. Okay, good. Thank you. So I got my time, I got my potential, and maybe I set the current, maybe I set a constant current equal to like 5 microamps, nothing crazy. And I have like, if this is 0, I have like no potential. But then I shine light, and at certain times I'll end up getting things like this. excuse my drawing. And so each one of these sections here is like the light is on, and then the light is off. Light is on, light is off. So that is the use of chronopotentiometry as a technique, and figuring out what this is, like this distance, that becomes your that in a way is your band gap. So that's kind of a way of thinking about it. So this is equivalent to the band gap. Of course, this assumes that when you shine the light, the light is of sufficient wavelength to excite electrons into the band gap. But a lot of people, and what this is doing basically is the potentiostat is responding to just drive this amount of current. And so it's basically, if you change this number of current, the potential is also going to change correspondingly. So you may have to be careful about what potential you need to apply, but you'll definitely get some information about the energetics of getting photocurrent to show. So maybe that sheds a little bit more light of, hopefully that shares a little bit more light into the use of chronopotentiometry for a photocatalytic semiconducting type of system.
That's a good pun, by the way. I like it. Shed some light.
Shed some light. Yes, that's right. Literally.
Yes.
Yeah,
the only other thing that comes to mind is if the chronopotentiometric analysis is such that you're applying for a set period of time and watching for the voltage to drop or something. I don't know how this coincides with the light on and off. What you just described makes more sense, that toggling the light on and off will change either the photo current, right? In this case, it's not, because you're setting the current. So it changes the measured potential, which is at least either equivalent or related heavily to the band gap, which is relevant for a semiconductor. But if you're talking about degradation, for example, is a degradation of the material or something like that, I suppose that would be accompanied with some dramatic or, I don't know, maybe gradual decrease in the voltage or increase in the voltage, something like that. So perhaps what you're looking for is drawing some amount of current or for some period of time and watching for the voltage to reach a state that indicates the material has degraded. And then you could say that amount of current over that amount of time is some amount of charge. And that would be roughly equivalent to its capacity before it degrades. I mean, these are just thinking out loud. I don't know, something like that.
No, I actually think that chronoamperometry may be better, like holding the potential and then watching current go up and down. Personally, I think is a better way to go about it. Okay, we have a question from Ben. Let's see. So Ben is saying, hey, while I'm preparing a seminar about cyclic voltammetry, I watch your videos about CV. How could I calculate, if I can, a Nernst standard potential from peaks of the voltammogram? It's a great question. So there's a couple things to keep in mind. So I think you already know from watching, and I'll share my screen because I think Neil knows this is like my favorite subject of all time, which is the Nernst equation.
That's right. Yeah.
Don't know why I love the Nernst equation.
The Nernst equation's your favorite. It's just, hey, everybody's got to have a favorite. It's fine. It doesn't make you weird. It doesn't make you weird or nerdy at all. Don't worry.
I think it makes me like the nerdiest.
Yeah, well, it actually very much does. Yeah.
Yeah. And then I think it's like RT over NF, and then we got the natural log. I'm actually getting much better at memorizing this equation.
Yeah, you really are. Every time I draw it now, I still like Google it really quickly just to make sure I don't screw anything up. I mean, it's not like if push came to shove, I wouldn't be able to figure out the Nernst equation. It's just more like, well, just in case I don't accidentally put the wrong, I don't know, constant or something.
Oh yeah. So I think, Ben, you understand, like, okay, this is the Nernst equation, and you're trying to solve for this, and you want to make sure that this whole thing is basically zero. So the concentration of this species and the concentration of this species are equal to one another, right? So this whole thing is equal to 1, right? That's what you're trying to do. So your question is, all right, well, where on a cyclic voltammogram, or can I use a cyclic voltammogram to figure out what that potential is, right? There's got to be some point on the voltage versus current where this is the case. And to do that, I'm actually going to show you something totally different. And let's see if everyone is all right. So let me share another thing. So let me share this. So all right. So I'm going to show you, this is our cyclic voltammetry simulation software. Okay, so I can simulate electrochemistry and voltammogram. So let's say we have a nice E0, a simple 1 electron reduction reaction. Okay, actually, let's see if I make this oxidation simulate. Nope, I'm going to make it reduction just to make things simple. Okay, so what I can do is I'm going to actually run this. It's going to kind of animate. And what I'm going to look here for is the surface concentration as a function of time. So I'm going to try to pause this. All right. So I kind of didn't get it super correct, but let me. All right. So you see here at this point, let me make sure that I'm going to hide your question temporarily so that it's easy to see. But if you look at this point right here where my mouse is, where these two cross, this point is when the concentration of species A and species B, which are the two like oxidized to gain reduced and reduced that can get oxidized species are. And it's when these two are equal to each other, which is this intersection, that, they're both 50%, that is where that's basically the point where the redox potential is, right? That's where your E0 is. And if you even look here, this is the E0. I've set it as 0 in this case. But if you kind of zoom in, which I'm gonna do here, and I'll make this a little bit bigger so everyone can kind of see. The E0 does not fall at like the peak. It doesn't fall at the tip. It actually falls closer to like 70% of the way, right? So that's a thing to keep in mind. So from a cyclic voltammogram, what a lot of people do, and in textbooks, you will find that, oh, your E0 is actually closer to maybe 70% up and down the oxidized and reduced forms. And so if I continue doing this, and if I also just keep an eye here, I'm going to try to make this go just a little bit faster so that let's see, it's faster, and then I'm going to slow it down. And of course, I missed it completely, but there's a second part. There's a second part that's right here that corresponds to like this point, again, like somewhere around 0. And so once you really hone in on where this 0 is on your voltammogram, this point right here, in this case, it's like 190 microamps. But like this point right here, not the peak, but that point is where these two concentrations are equal to each other. So that is, and some people really estimate this as about 70% or so up. So hopefully that is how you do it. That's a way you can kind of determine the standard potential for doing a CV experiment. So Ben, I hope that this was helpful. And
Is there a I don't know, like, how does what you just like, that's a I don't know how to put it. That's a better, probably more thorough answer, because
yeah.
like the strictly by the Nernst equation, which is related to the question, which is correct, right? When the natural log is 1, that's 0, and then E equals E0, right? But how accurate is that estimation compared to just splitting the difference between the oxidation and reduction peaks?
Oh, you mean like the peak potentials? And
Yeah,
then
like
by
I guess
half?
that's like right, yeah. E1
Right.
half being so that's people tend to do
Yes.
that as an estimate, right? So you have your oxidation peak, you have your reduction peak, and then halfway between them is E1 half. That's roughly E0 also sometimes, right? It
Yeah.
depends how reversible it is. So what's what's the
Oh,
correlation between what you just described and that method?
yeah. So that's a great question. Let's do it. I actually started doing it and I forgot to share the screen. So I literally just took the voltammogram that we just saw, and I'm going to use the crosshair tool here.
Yeah, get these
And
peaks and
so that's about this is a great learning experience for all of us. Okay, great. So we now have a value, and this value 28
28.
millivolts. Okay, and then let's do another one of these. So tool crosshair, and I'm gonna move it around a bit so I can see. All right, and then I'm gonna put that guy here. Oh, we have the best tools. Okay. Why is this
Too soon.
too soon? So
Minus 20.
actually, it's so you're right. So you get a so in this case, actually the
Zero.
difference in the peaks actually works out to be very pretty good because they're exactly equal and opposite from one another. Now, of course, you're assuming fast kinetics, all that kind of stuff. So yes, the peak, I guess you could say the difference in the peak potentials. So it's like yeah, they're equal and opposite from 0
In this case,
to
E1 half is just actually 0.
yeah. In this case, E1 half is 0. So yes, you can use the
So
difference
E1
between the
half in
peak.
this case is maybe it's accurate to say something like this: E1 half, which is the difference between the peaks, will equal E0 if and only if it's like the best kinetic reactions, something like that.
Right, right. And some people will use these to figure out like a quote E1 half, but you're right. It is the case. So we could do that in a way. Let's actually I
Change
am
some of those
curious.
kinetics.
Yeah, so we can change the kinetics. Let's make this slower. Simulate. So it's clearly slower. You can see the difference here. And then let's archive that guy. And you folks at home, you can do this too. We have simulation software that you can go onto our website, aftermathlive.com, and you can play around with all these super cool tools and do simulation, not only to learn electrochemistry, but then also figure out exactly, and then you can even fit or simulate your data. So, and then let's go to crosshair. Now, of course, also this is like perfectly theoretical and works very well.
Now it actually does.
There does
show
seem
its
to be
discrepancy, so
some
that's good.
differentiation.
Yeah, you got 120 on one side and like 112 on the other. So it should be 0, but it isn't. Or whatever, right?
Yeah, but it's still very, very close. Like, this is
Yeah.
is this exactly the right thing?
Yeah, give or
Maybe
take.
give or take. But that's still pretty good. I mean, we're talking about like
Yeah.
I mean,
but
we're
I
talking
mean,
like
the
few
real
millivolts.
accurate way to do it would be to find where the reaction quotient is unity.
Yeah.
Because mathematically, that's the solution of the Nernst equation, whereby the E equals E0.
Yes. Yeah.
This is a cool visualization, though.
Yeah. This is a way, and of course, like, I mean, in a way, we're answering electrochemistry questions, but this is a great, like, this tool is super useful for learning electrochemistry. Like, it's a great research tool, but it's also, it's really good for just learning, like, what happens when the solution resistance is super, super high? I can simulate that. What happens if the diffusion coefficient is super slow? I can simulate that. If I have an electron transfer plus a chemical step plus blah, 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 I can simulate that, and I can actually see what does that look like. So I think it's I'm biased, right? I think it's great because our company made it.
Well, if you want a different opinion, I have one. I also think it's great. Sorry, that's the same opinion. I'm sorry.
Marimus is actually more about chronopotentiometry. I do want to make a video actually about chronoamperometry. I can focus a little bit about chronopotentiometry, but
So the list that I have for my next webinar series, which will probably be completed at this point in the next 35 years,
right.
is a voltammetry series. So I wanted to do it sooner. I wanted to do it like 6 months ago, but that didn't happen. So anyway, probably sometime early in the year of next year, if I can get the materials put together, I will be doing a voltammetry series webinar. And it's going to be like probably 2 or 3 weeks, 2 or 3 sessions long is my guess. And so I'm planning tentatively to cover like cyclical voltammetry,
Yeah.
and then probably chronoamperometry, chronopotentiometry,
Pulse techniques,
and then
like
pulse techniques. Yeah, exactly. So it's probably going to go only as deep, if you will, as pulse techniques, as far as the complexity, if you will, right, of voltammetry. And in some ways, it's I don't know, complementary to like Alex's video on cyclic voltammetry, which you said that Ben, you said you watched, I think, right? So it's like a lot of that content will be similar, but I guess the point is to sort of discuss just some of the differences and mathematics and theory and application of different forms of voltammetry. But I guess to your question, Murray, is that we don't really have grand plans to make like videos on every specific technique. It's quite a lot. Right?
I do. I have grand plans.
Well,
I have massive plans to make videos on everything.
Well, then I shouldn't speak for you, my friend.
But
because,
it'll take a long time.
Yeah, your ability to output videos is related to my ability to output webinars, which is to say it never happens because we're just busy with other stuff. So in a perfect world, we would have all the times, and we would be putting out all of this stuff, and it just like, the perfect world doesn't exist, unfortunately. But so maybe at some point we will be able to cover some of that.
Yeah, eventually.
So keep in touch with us, and at the very least, it's sort of like a circular answer, but I always tell people what resources can I have? Well, that's exactly what we're doing now. We're trying to give you this resource right here. We're certainly not perfect, and we don't know everything, but that's why we're doing this, because I don't think there's a lot of readily available electrochemistry like resources out there, perhaps for the average student who's just kind of trying to find their way and is finding graduate school difficult or what have you. So
yeah, definitely. I think there's a lot of resources. I just don't think they're very easy to understand.
The textbook, that's why I hesitated to even mention, like, Orzum is brilliant in his textbook. So is Lassia. It's just like the average graduate student, and I felt this way when I was in graduate school, like, oh, well, you want to learn something, just sit down and read a textbook all the way through. It's like, man, as if attention spans were bad enough when we were in graduate school a decade ago. They've gotten worse. And I'm not saying I want to like necessarily give in to that, because you want to think that people would be open to studying and everything, but the reality is what it is, right?
Yeah, I also think I picked up Orzum's textbook today just to like try to read things, and a lot of these textbooks, honestly, like, they're very thorough, very detailed, lots of theoretical stuff, but it's very hard to bridge the gap between like theory, hardcore mathematical theory, and practice. And what's kind of useful. So
there is definitely a disconnect between reading it all, and then I think I've described this phenomenon because I felt this way when I was in graduate school, where it's like, because I was in a group with a brilliant advisor, and he's awesome, and he was an electrochemist, and he knew everything about everything. And like, before getting started in the lab, like, he basically gave me like, because I joined the group and I'm part of the group when we're doing electrochemistry, and he gave me like lectures, like one-on-one, like here's the basics of electrochemistry. He taught me the Butler-Volmer equation, the Nernst equation, everything, control equation. You do all of it, and you learn little basics about all these techniques. And we did that over, I don't know, couple weeks, multiple sessions. Like it was a mini course just for me. And it was like, I took notes and I understood it to a certain extent. And then it's like you get into the lab and you're staring at a potentiostat with this cell cable and a bunch of alligator clips, and you're staring at a platinum foil, and you're staring at an electrode and a rotator and a fuel cell, and you're staring at all the stuff, and everything that everything that you had in your notes just goes right out the window. You're sitting there, you're like, I don't know what to do. I don't know. I got nothing. I know that E0 natural log of Q is a thing. Like, what does that help me? Right. Ultimately, the lack of just like, and maybe that's part and parcel of graduate school. Like the answer could just be that everybody has to kind of suffer a little bit, right? Because that's how you learn, is through struggle and, repetition and practice and stuff. But I do think that there's something to be said for the perhaps anxiety and maybe even panic in some cases that graduate students might feel when they get into the lab, and they feel so lost. They don't know what to click, what to push, what to connect, what to do. And it's like textbooks just can't bridge that gap.
Yeah.
They just can't. Not to take anything away from their use, right? It's just that the practicality, there's some missing piece perpetually, I feel, with graduate research,
Yeah. I do want to know, Chris, if you want to type a little bit more, I do want to know about what your ideas are about a series, Applied Electrochem Beyond the Lab. So I am curious what would this series entail? Because we like you, and we want to know a little bit more about your ideas.
Is this like Bed Bath and Beyond, except it's like Nernst, Cottrell and Beyond or something?
Yeah, that's right.
Beyond the Lab.
Beyond the Lab.
Yeah. Can we Bed Bath and Beyond went bankrupt, I think that happened.
I think so.
Okay.
I think
So hear me out. You know the movie Click? Have you seen the movie Click? Adam Sandler.
Oh, with a remote that he can like change.
Yeah, he has a remote. He changes his life, and he fast forwards through the boring parts, and then he fast forwards his entire life, and he's like, oh, I shouldn't have done that. Anyway, he gets the remote from the Beyond section in Bed and Bath and Beyond. Okay. All right, now hear me out. They're bankrupt. Okay.
They're bankrupt.
So does anybody own that
clicker
IP anymore? Can we just steal it? Can we just make a Bed Bath and Beyond electrochemistry beyond? Can we just brazenly steal it? Are we gonna get in trouble?
That's a good question. I actually
what happens when the company goes bankrupt? Is I don't know how this works.
Happens to their IP?
Copywritten or patented? Like, you know what I mean? Like they have, that company presumably has or had some patent or copyright on names and logos, but they don't exist anymore. So can we steal it?
Yeah,
because that would be a fun, video series or whatever. If we could do like Beyond the Lab and just steal the Bed Bath and Beyond logo, but make it Echem or something. I don't know.
Actually, I was thinking you were going to go down the route of looking at like defunct electrochemistry companies and how did they, what was the process of like their decline and like what happens to their IP afterwards.
No, but that one's a little less mysterious because like EG and G became par, right?
Oh,
and then,
okay, yeah.
Radiometer is Aurigelis now, although it's maybe not entirely. Like there's a company in France called Aurigelis. They make rotators, and that was Radiometer some time ago. So I have a very limited knowledge of that, like anthology of various electrochemistry. But also, I mean, you and I are like literally the same age. I don't know what our boss was using in 1890. Sorry, not that long ago. I'm just teasing. No, but I don't know obviously what exactly like commercial equipment people were using in the 50s or 60s or whatever it was when they were doing mercury drop and chart recorders and all this kind of craziness. Yeah, but, I mean that's an interesting thing though, to do some kind of
I am thinking about like just what happens when a company goes bankrupt, and that just requires a whole law thing. If anyone out there knows any lawyers who know what happens, please let us know because we're just curious, and you can share
Are
it
there
on the
any
next
are there any concurrent YouTube live streams like Ask Us Anything about
law.
bankruptcy and company names? Can we join and ask?
I know that there are a lot of there are definitely a lot of like law YouTube channels that just talk about like just random legal stuff like bankruptcy
Yeah.
law, divorce law, suing your neighbor, just like all those types of things. So, oh, but
Do they,
Chris is actually giving us a little bit more detail. Maybe we were really off. Well, getting into actual practical applications of electrochemistry in industry, plating, battery storage, and water treatment, sensor semiconductor. Wow, we were off. We were off
no, we weren't off.
so
I
much.
wasn't off. That's wrong. I was right. It's ripping off the Bed Bath and Beyond for some video series is exactly what you meant. That's what
Who,
I understand.
who is Steve Leto?
Steve
I don't
Leto.
know.
I don't know who Steve
Yeah.
Leto is.
Steve Leto Law. I don't know, but it looks like it's a
Oh, is he
law.
one of these people that does? Is it like financial YouTube people who basically give advice and they're like, I'm not giving advice, but here's what you should do.
Yeah,
So they're
yeah,
like not legally liable. So these people are like, well, I'm not a lawyer, I can't give you any advice, but here's all my expertise.
yeah. That's right. You know, I do sometimes wonder. Like, I bet those finance YouTubers could probably get like a CFA or some kind of certification. Then they could actually give legal advice.
I think the
But then
tricky
they
thing is that it varies by state, right? Like for the United States
oh
in
yeah.
particular, like so if you're doing a YouTube thing
Mhm.
and you're in California, you need a CFA license. But if you're
Yeah.
helping someone who's in Tennessee, you don't have to. But then someone in Wisconsin, it's like there's something to that. I know that
Yeah.
generally speaking, the rule of thumb, because you and I like some YouTube or whatever finance kind of things
Yeah.
too.
Yeah. Yeah.
There's like they pepper in. They'll go, you know. 20 minutes they'll talk about a thing and all of a sudden they'll be like, by the way, this is not financial advice. It's like they have to like pepper that in
Yeah.
like a tick, but it's
Yeah.
because
Yeah. That's right.
there's some legal requirement where someone could like be like, I lost all my money and it's your fault or something.
Oh yeah. Yeah.
So it's
Absolutely.
like they say, no, you know, I uh, I am not a person who's helping you, even though I'm giving you advice. Whatever. This that whole like legal for whatever the legality of it is, which obviously I don't know.
Yeah. Yeah. Let's see.
Oh, interesting legal bits.
Yeah. Just as interesting legal bits. Okay. Okay. Well, I think I don't have any questions now, but how's your trip been so far? We can wait a little bit longer while we
Yeah, we'll wait a little bit and then we'll.
yeah.
Yeah, it's fine.
Are you at the
I was
airport?
just at a conference for the last couple of days. I'm near St. Louis, Missouri, at a regional meeting of the Electrochemical Society. No, of the American Chemical
American
Society.
Chemical.
Excuse me. Yeah, ACS. So the American Chemical Society has regional meetings around the United States, hence the A in ACS, and yeah, and so it's a short, few days meeting, and so it just kind of wrapped up, and I was able to pop on here. But it's good. I met a handful of people, and the ACS meetings are kind of nice. You get a little bit of a different crowd than the purely electrochemistry folks at something like ISE or ECS. So
Mhm.
the ACS meetings are right more general chemistry, let's say. So a lot of the folks who come to ACS meetings are they might be doing electrochemistry, they might not be doing much electrochemistry, or they might sort of need to do electrochemistry and they fall into that category of like they don't know very much about it and it's a new topic. So similar to this live stream, I guess
Mhm.
it's a phenomenon of um, people are needing to do uh, electrochemistry but not really sure much about the logistics or the theory or what have you. So
Mhm.
so it's kind of fun. I mean, I like it because because yeah, it's just a different crowd of people to meet. And it's often new folks. Because sometimes at the ECS meetings, which are nice and fun, but sometimes we see the same people, and it's nice to meet new people who are coming into the electrochemistry world, kind of getting them into the fold or something like that. So
yeah, and I was at the ECS meeting in Sweden. I think it was last week, and yeah, a lot of familiar faces and a lot of just a lot of like really intense electrochemistry like questions that people ask, and most people at the ACS are like, I just need to do a cyclic voltammetry experiment. It's like, hey, we can do that.
Although here's two fun little tidbits that I learned at this meeting. So the first is that a gentleman stopped by my booth who was looking into like corrosion, and so corrosion is a pretty common electrochemical process, of course. When you're talking about steel, metal, whatever, right? That's like rusting. It's an oxidation. But he was talking about basically corrosion and degradation of wood. And I'm like, okay, well, that's interesting, but probably not related to electrochemistry so much. It's, wood is basically cellulose. It's not electrically conducting, to the best of my knowledge anyway. And he gave me a reference and showed me actually that when wood is wetted, when it gets really wet, I guess it actually conducts.
Interesting.
I don't know, like of course, there's 1.5 million different kinds of trees, so this may not be like, does a pine tree do it? Does whatever kind of wood or every kind of tree? But I guess it's related to, if they make boats or various materials that are made out of wood with like metal fasteners and things. So you'll have degradation of either the wood and or the metal.
That's a good point.
And things like that. And so electrochemistry might be a way that people can effectively measure some of those processes, because obviously electrochemistry is done with aqueous quite often or in water. And so if it's wet, it might conduct enough to be able to do impedance to measure the resistance or something like that. Yeah. So that was kind of interesting. I didn't know that. And then the second thing I learned is really disgusting.
Yeah. Oh boy.
Is that mucus for so mucus in your nasal cavity, in your throat or whatever.
Oh boy!
So I told you. Listen, I told you it was going to be gross. I'm now in. You can't blame me for anything I say now. I told you it'd be gross. But apparently, bacteria is negatively charged. I guess I don't know if that means all bacteria, but some bacteria is apparently negatively charged. And so one of the ideas, I guess, that this woman had, either she's doing it or it's an idea for some proof of concept, is that one of the main mechanisms by which like mucus cells can prevent disease or whatever is that they trap pathogens, right? And so then when you expel the mucus, it doesn't end up in your bloodstream, whatever. So this is a pretty well-known thing, but basically the mechanism mainly by which that happens is it's just extremely viscous, right? It's a matrix of viscous material, and so stuff will get stuck in it. This is pretty obvious and evident. The problem is that smaller bacteria and pathogens can move right through unimpeded because they're small enough to move through the matrix or something. Yeah. And so anyway, if the charge or the electrochemistry can be used potentially is sort of the open question to facilitate like blocking of certain pathogens. So for example, and this is an open question, if bacteria is negatively charged, if you can have negatively charged mucus, it would repel it potentially, or positively charged mucus would bind it, like it would do something of that nature. So there you go. There's your disgusting fact of the week.
So does that mean we're gonna have like electrodes connected to our nose and basically like, all right, you're sick. I have some vitamin C and sleep, and connect the working electrode to the left one and the reference electrode.
You're not feeling well. Let me take these two electrodes and stick them up your nose. And it just zaps you with a positive current all day. and it just takes all the bacteria and just goes in.
Yeah.
See, you've heard
Oh.
of glucose strips for electrochemistry in the real
Yeah.
world. Well, this is next level biological electrochemistry.
Glucose strips, mucose strips.
Yeah.
Actually, Neil, this you might like this. I got a question. I haven't fully like wrapped my head around it. This was at the Electrochemical Society, and so this guy, it's a very interesting question, or a very interesting system. So he's got an electrode, right? Let's call this electrode. Electrode. And what he has is he's got these two nanoparticles. He's got one nanoparticle here of like platinum, and he's got another nanoparticle here in contact, they're aggregates, of iridium. Okay. And he's doing, I think he's doing like OER or something like that. He's doing like OER. And he's doing impedance.
Mhm.
And what he knows is that like he can get oxygen evolution on the iridium, right?
Mhm.
So OER is happening here at the potential he's applying. But it's not happening here, right? So that's not happening. There's no OER on the platinum. It's just on this iridium. Now, this, when we look at this, the electrical double layer, which I'm going to just kind of mark as this, is like it's on platinum. There's an interface of, double layer, but it's also on iridium. And like the double layer doesn't care if it's like platinum or iridium. It's like slightly different structure. But he's thinking like, hey, could I actually elucidate information about, like, could he kind of separate these two things in the impedance world? Like, could I understand what the capacitance of platinum is versus the capacitance of iridium? Because in a way, he has a circuit where it's just like, okay, resistance and then capacitance for platinum. But he actually has like resistance and then
Randall's element.
a Randall's element for the iridium. And he was wondering like, all right, is there a way he could actually decouple like these two things? Is that even possible? And so I was like, I'm thinking about this, and I'm like, oh, I've never thought about like, all right, your double layer kind of is all over the place. Is it even different between these two? But it's like this is a situation where only a part of your electrochemical system has your charge transfer resistance, but the rest of it kind of doesn't. And he thinks the chemistry on the electrode, the chemistry on the platinum is different. So mucus electrochemistry versus like this is the difference between American
Okay.
Chemical Society electrochemistry.
Yeah,
and
exactly.
Electrochemical
You're
Society
dealing with like
electrochemistry.
you're dealing with extremely complex, convoluted electrochemistry stuff, and I'm dealing with snot.
Yeah,
So-
yeah, I know. It's just like I was like, it's a great question. I'm like, I don't know if
So
know
I
if you
think
could
the
deconvolute these
answer
things.
is most probably no,
Okay.
for a couple of reasons. First of all,
Yeah.
fundamentally,
Fundamentally.
iridium is a better OER catalyst than platinum, I believe. So that tracks with the ability to likely pick a potential that will catalyze oxygen evolution on iridium, but is too low for platinum, because platinum probably has a larger overpotential for OER than iridium, because it's worse.
Yeah.
Platinum is actually, it will do OER, obviously, if you have platinum and you just go high enough, but platinum is generally not considered to be a good OER catalyst. So, so that part is tracked. It checks out, probably is fine. The problem, first of all, is that practically from a resolution perspective, trying to get spectra on a single nanoparticle is just ain't gonna happen. Sorry, ain't gonna happen. If you have a series of those nanoparticles and you know that the structure is such that they're all touching exactly like that, and you have some sort of direct ability to know that you can correlate capacitive effects and OER effects on one compared to the other, and your surface is as such, okay, then we could start having a conversation, because you need to have appreciable amount of capacitive buildup, current
Yeah.
response. Like, what do you honestly think the current is on a single nanoparticle?
Oh
Like
yeah.
a millionth of a
Femtoamps.
millionth of a femtoamp? Like, there is no potentiostat capable of measuring the current associated with a single nanoparticle accurately.
Well, don't say that to Jeffrey Dick. He's gonna be like, he leads the charge on like nanoparticle electrochemistry.
Via impedance. It's very hard to do this
Yes,
via
via impedance, very very hard. Yes.
So yes, I do know that your Dick is doing cool stuff with like trying to like spit a single nanoparticle at a thing and seeing how it causes a jump in the current or whatever. The point is that even if it's possible, it's very tricky, and I would the amount of your ability to quantify signal to noise in this would be really, really difficult.
Oh yeah.
But the second thing is that while oxygen evolution is only taking place on one, part of your catalyst, there is likely some unbroken double layer over all of it. So the fact that the OER is occurring through the double layer on just the iridium does not necessarily guarantee that you would be able to isolate the double layer on just that part of your catalyst.
Yeah.
I suspect that it would not work that way. And the last thing that I can say about it is that the proof would simply be in the experiment, right? It's if your data looks that it could be fit with disparate capacitances, right, for whatever the spectrum would look like. For example, if your Nyquist plot, your Bodhi plot, whatever, if it is manifesting in a way where you could make that argument, then maybe. But even then, I think it's a bit of an assumption,
Yeah.
I
agree.
I'm just trying to think like, yeah, I don't know that the because like the parallel formation of oxygen evolution, a faradaic process occurring through the double layer capacitance, like that capacitance, like you can't escape that capacitance is being measured everywhere. It just is.
Yeah.
Like, you know what I mean? Like if you were to get the fitting of that capacitor, what makes you think it's just on the iridium? Because there's capacitance everywhere, and it's all conductive, and it's all part of the electrode.
Yeah.
So I would doubt that you would be able to say like, oh, well, the capacitance, this part of my circuit is like just on the iridium. It's like, why? There's capacitance everywhere. Why would that be only I don't know. I have doubts that it would be like a perfect bifurcation that you could fit that way. It's interesting. Like,
Yeah.
for sure.
It's an interesting
But
question.
from that perspective, I don't know that would work.
Yeah.
I think there's a couple other questions.
Yeah, we got a couple questions. One is from Little Research. If negatively charged nanoparticles increases specific capacitance of activated carbon electrode, what will be the reason? I have added negatively charged nanoparticles in 3 molar potassium hydroxide. So the specific capacitance increase the specific capacitance.
Well, you have a negative charge on your
nanoparticle.
Yeah, a negatively charged nanoparticle with your carbon. So you're sort of like doping your carbon with some extra, charges. It's not surprising that you would have increased capacitance. Capacitance is in this context, just like what we were talking about before this with double layer, you have if you have a negatively charged electrode, you have positively charged ions, solvated ions. There's a lot more to it, but basically, positively charged ions are lined up at a distance from the surface, and so the more that's going to happen proportionately to the charge at your electrode. And then, generally speaking, carbon can be improved in its electrocatalytic activity with dopants. So sometimes either direction too. You can have basically electron donating or electron withdrawing dopants like boron or phosphorus or nitrogen or whatever. You can dope carbon with stuff and it will improve its activity, improve its capacity, because sometimes it creates defects. It creates stronger electronic conductivity and stronger charge, which leads to more capacitive effects. So this is all pretty normal, I guess. Doping of carbon and things of that nature do often improve its electrocatalytic activity.
Yeah, I need to actually look up like specific capacitance and specific capacitance per unit mass versus like capacitance per
Or
unit area. Yeah.
Oh, I guess it could be either. Specific just means it's with respect to something, but
yeah,
that always means area or
mass.
But I mean, it's like the same amount of carbon with a dopant will probably behave better than the same amount of carbon without a dopant. So it will have a higher specific capacitance.
Yeah, and you're adding a lot of negative charge. So and the carbon surface, the activated carbon surface by itself might not have a lot of negative charge. Negatively charged nanoparticles, probably, I'm assuming they're metal, right? That's just maybe an assumption. But that would also be another reason, like metal nanoparticles have a outside, like they have negative charge on the outside typically, or they're negatively charged actually. So, and let's see, a little research just given says nanoparticles are added in KOH as additive. So Neil, I think this is to support your as additive. So I think this is.
So I had it backwards as a dopant thing.
But it's nanoparticles are added in KOH as additive. So, but it still might dope it. It's on the surface, right?
Yeah, I don't know what kind of interaction the nanoparticles are having with your carbon. They might be behaving similarly to the phenomenon I just described, which is that they are not exactly doping. You haven't like changed the carbon itself, but because they're in solution, some will make their way to the surface and they might be acting as a sort of a dopant in that kind of experiment. I'm not sure though.
Yeah. But sorry. No, I do think that there's a lot of charge. I think there's a lot of charge on metal nanoparticles, and I don't know what kind of nanoparticles there are, but it doesn't surprise me that per mass you're getting more higher capacitance because you're adding charged species, which affects the double layer. So hopefully that helps.
Yeah.
We have a question from Tafara. Tafara says, "Hello guys, I have a question. I'm an undergraduate doing research on electrolyte additives that stop ionic transfer during thermal runaway. Following up, I want to show with impedance that when the additive and electrolyte react, there is a decrease in ionic conductivity. At my university, there are limited resources, and I want to do this on a potentiostat." And then he says, "But I only have two platinum wires as electrodes." So, Tafara, I will say that if you don't have a potentiostat, you can definitely if you don't have a potentiostat, I think it's going to be very, very difficult for you to do impedance. like you can't really like if you would need first off you need to have some kind of waveform generator just to start off with, right? Like you need some way to apply a sinusoidal wave if you want to do impedance in general. So, and I think the nature of your experiment, it sounds fine. Use impedance. Look at an increase in the resistance, which tells you that there's a decrease in the conductivity. Perfectly fine
Yeah,
experiment.
you also don't necessarily need impedance to do this. So if you
Mm-hmm.
and if to Alex's point, of course, if you have a potentiostat, it will be much more, uh, helpful to you to be able to control and measure things. But if you only have like a power supply and two platinum wires, the best thing that you'll be able to try to do is very slow sweeps right around the open circuit, something like that. So apply a voltage across the two wires and measure the current. Yeah, something like that, or you would do that over a very small range. So you would want to try to find the voltage. You'd want to try to find close to what the open circuit is. You want to find the voltage where you're not measuring any current.
And you
However,
can use
you're
a
able to do.
voltmeter for that.
Yeah, exactly. You could
Yeah.
use a voltmeter or like, I mean, a power supply, and you're just adjusting the voltage until you're measuring no current. Whatever devices you have available to you, and then you're just going to basically apply a few steps around the open circuit and measure, and then you're just doing Ohm's law. And so that's a relatively crude way to get like V equals IR. You can measure the R, and so adding in your additive, how does it increase the resistance, which would be a decrease in conductivity?
Yeah. Yeah. I think that's
And that's an interesting idea. I assume you're talking about a battery because thermal runaway is the decomposition and failure of a battery. And I'm interested to know how that would even work, because dramatically decreasing the conductivity ionically would probably have a very detrimental impact on the functionality of the battery. So unless your idea is to have it as a fail-safe, which essentially upon thermal runaway beginning, it would dump your additive in to facilitate the reduction in conductivity, but only when it's failing. Because one of the problems of batteries can be that it's a non-aqueous solvent. You have to pump a lot of like LiPF6 in it to make it function. Any decrease in the conductivity will make it struggle, right? So if you're doing that intentionally for a safety reason, I understand, because batteries are dangerous, and when they go into thermal runaway, it's a self-driving process. In other words, it burns itself out. It's why they're so dangerous. Okay, so fail safe. So it's like there'd be some like pod inside, kind of like how you have a positive temperature coefficient or like a CID. This would be like a pod inside that would like rupture and spill additive into the electrolyte to reduce its conductivity upon an increase in temperature or something of that nature. That's a smart thing to do, because a positive temperature coefficient is a good safety feature for a battery, but it will only stop the electrical connection when the temperature rises. If the temperature is rising not because of the battery management system or an attached electrical charge, then that won't stop it from continuing to fail. And then similarly, the vent in a current interrupt can do the same, but if it's already hit thermal runaway, then it's going to keep venting. It's not going to stop it. So this is a cool idea if you can find a way to basically destroy the fuel source, which is the battery itself.
nice. I
Microencapsulation on the additive. That's a cool idea. Yeah.
oh,
Pop in X number of months and tell me if it works. It's a cool idea.
Very cool. Yeah, I don't know as much. I don't know a fraction of the amount of knowledge that Neil does about batteries. So that
Yeah, I
is
studied battery safety when I was a postdoc, so it's partly why I was blowing them up. Look at what happens.
yeah.
Not necessarily how to fix it. As far as looking at how to fix it, I was just looking at what happens when they blow up.
Yeah.
A lot of fun stuff.
The ECS is they're almost finished with a battery like kind of micro course. It's like a 25-hour course trying to teach 3 sections teaching you about batteries.
Who's teaching it?
There's like 3 people. Let me see if I can get to if I have my notes from it. So there were 3 sections. One was from Lin Ma at the University of North Carolina, and his course is on lithium-ion battery components for short course development. It's based on this million-mile battery paper he wrote. The other part of the course is electrochemical techniques and diagnostics for batteries, which is led by Wes Change at Drexel, Jeff Lowe at GM, and Matthew DeBari at University of Hawaii. I might be butchering people's names. And then the last one's fabrication of batteries and pack design, which is led by Peter Dreher. And these are all like they've been working on this for I think some time to create like this course. I think it's getting relatively close to launching, but anyway, it's interesting.
Murray, how can you use impedance to know if it's N or P type? When you do Mott-Schottky,
Oh yeah.
if the slope of the Mott-Schott, this is if a rule of thumb to remember this is it's backwards. When you do Mott-Schottky, if the slope is negative, it's P type. If the slope is positive, it's N type.
And there
That's
you have it. That is it. Let's see. Chris actually has an interesting comment, which is we're just dumping a bunch of
What carbonate?
carbonate inactivate
Minus
the
2.
lithium.
CO3 minus 2.
Oh yeah. Well, yeah, he is.
Assuming 2 minus.
Yeah, 2 minus. Yeah, it'd be kind of hard to write like CO3 2 minus, and but yeah.
I don't think that would have any impact. I think your idea is to bind the lithium into some sort of insoluble salt, but the lithium isn't really the problem. The problem with thermal runaway is so much more varied that simply binding the lithium would have almost no impact. It's the electrolyte itself is like rocket fuel. Once it starts going, it's over. It starts decomposing. The anode and the cathode start decomposing. There's a lot happening that probably just binding one part of it wouldn't do a ton, is my guess. I could be wrong, but that's my impression. I think we'll wrap it up here. Does that sound good?
I think that sounds good. I think this is a good episode, and I guess Neil, we'll have to talk about next week because there's a lot of stuff happening next week.
Yeah, we have a lot of things. We might have to take a week off. I guess.
May have to take a week off. For
Maybe I can do it. Well, no, because we have a conference and we have some visitors. It's a bit much. We might have to give it a week.
Yeah, we may have to give it a week.
We haven't missed a week in months.
I know we've tried, but I mean it happens. I mean it happens. We can also do another time, or I can figure out like, oh, maybe we can talk more about the details and see what if there's room in the schedule and stuff like that. Well, we'll see. But people will know. I guess just a quick comment to Murray is just like, how can I do Mott-Schottky? Mott-Schottky should be a technique on your potentiostat. Where you can just kind of click the buttons. But in general, Neil, I think you do EIS at a variety of potentials.
Yeah, Mott-Schottky is a variation of impedance. You pick a potential, you do impedance, usually over a short-ish window of frequencies. And then you change the potential, you do impedance again. Change the potential, do impedance again.
Yeah.
So you can either do this with your potentiostat in your software. If it has a Mott-Schottky program, you pick an initial and a final potential and a step size. So you do every 50 millivolts from 0 to 500 millivolts or something.
Yeah.
And you're going to do like impedance. If the potentiostat is smart, it would have you do a range. A lot of them don't. They just have a single frequency point, which is quite inaccurate, but you can do it in a pinch if you need to. Otherwise, you can do it manually by simply doing a bunch of set points, like do an EIS spectrum at 0 volts, and then an EIS at 50 millivolts, and then an EIS at 100 millivolts. And you're doing that. The analysis is a bit much more. We're kind of wrapping up here, and I guess my ability to describe all of the ins and outs of Mott-Schottky are a little limited at the moment, just due to time. Join us at another one of these live streams. Is the best I can say right now. And I can kind of talk a little more in depth about how Mott-Schottky works and how the analysis works, but it is quite in depth, and I'm not able to really get into those details right now.
Yeah.
But that is how it's done.
Yeah. Yeah. I agree. And similarly, I'm also looking at this another question from Amar. Well, we can probably go into more detail about this later, like how to reduce non-faradaic current on ferrocene self-assembled monolayer using square wave. In short, you're probably going to want to just increase the step length of your pulse in your square wave, because the non-faradaic current components usually at the beginning, the charging of the capacitive element happens very rapidly. The diffusion faradaic current happens more slowly. So to decrease the relative amount of that, I would try a longer step size. Your experiment will take longer, but
longer step size, or what is it? Increasing the period or something, or whatever the settings are.
Whatever that setting is.
It's another tricky thing to. Again, if we had more time,
I
would get into the details. I have a thing on square wave as well, but basically. That's it.
Okay, I think that is all. Thanks for joining us, and we'll see you later.
Yeah, either next week or in 2 weeks from now.
In 2 weeks.
But, cool. All right, everybody.
All right.
Take it easy.